Hello everyone, this is Wenjun from USSLAB, Zhejiang University. I'm going to introduce our paper, TPatch, a triggered physical adversarial patch. This is joint work with Tsinghua University. In recent years, the technology of autonomous vehicles is booming. Visual recognition is one of the main techniques for an autonomous vehicle to perceive its environment, such as traffic signs and obstacles, and then make the correct driving decisions. So its reliability is critical to the driving safety. For example, in 2020, a fatal traffic accident of Tesla was caused by failing to recognize the overturned track on the highway. Much work has been devoted to analyzing the reliability of visual recognition. Among them, researchers have demonstrated that adversarial patches can lead to incorrect recognition results. For instance, adding a patch to the stop sign can hide it, or placing a standalone patch can create a fake stop sign. Those adversarial patches affect all passing vehicles because they are placed in the open world and always activated. So in this work, we ask a research question: can we design an adversarial patch that can affect one of the passing vehicles rather than all of them? Our basic idea is to make the adversarial patch triggerable. Let me show you a TPatch attack scenario. The adversary ports a TPatch at the roadside, which is benign to most passing cars, but can render the target car that receives the triggering signal to recognize a non-existing stop sign, resulting in a sudden stop and a possible rear-end collision. Particularly inspired by pyrosensor attacks, we inject acoustic signals into the target car, thus blurring its captured image, and then the blurry patch will be in the triggered state to achieve various attack goals, such as hiding, creating, and altering. So how to achieve TPatch? There are 4 challenges required to be resolved. First, how to make the acoustic signal reliably trigger the patch. Second, how to ensure that TPatch is only triggered by acoustic attacks. Third, how to make TPatch appear less conspicuous to humans. Last but not least, how to improve the attack robustness in the real world. Eventually, we designed 4 building blocks that correspond to 4 challenges to generate TPatch. In the following, we introduce their details one by one. Before introducing the signal design, we will briefly introduce how acoustic signals can affect cameras with an image stabilizer. The adversary launched this attack by injecting resonant acoustic signals into the MEMS inertial sensors, thus causing fake inertial readings. Consequently, the image stabilizer controls the movement of the camera lens to compensate for the fake camera motion, which on the contrary causes camera motion blur. To serve as a trigger, the resulting motion blur should be consistent. However, from the generation of blurry images, we can see the resulting motion blur is often time-variant and depends on when the shutter is open. Given we are unable to synchronize with the shutter, how can we make the motion blur consistent? To solve this challenge, we designed the attack signal frequency as an integral multiple of the sampling frequency plus or minus the exposure frequency. Because of aliasing, the resulting inertial reading becomes a sine wave with the exposure frequency, making the camera motion frequency also equal to the exposure frequency. Thus, the resulting motion blur becomes time invariant and doesn't need synchronization. Next, we model the resulting blur. The acoustic attacks cause a combined sinusoidal motion in 2 dimensions. And in practice, the phase difference between the x-axis and y-axis is trivial, so that the resulting blur becomes linear. And then we build a 2D coordinate system to describe the linear blur with its strength and orientation. The second challenge is how to enable TPatch to be only triggered by the injected blur rather than the unintended blur occurring in normal driving. To investigate the feasibility, we use an estimation-based method to obtain their blur kernels from real-world images, and then place them into the 2D coordinate system for comparison. We find that the inject blur is unusual in normal driving, and thus it's possible to exploit the differences in strength and orientation to trigger TPatch. Well, to optimize the patch, we define two types of triggers. One is a real trigger, namely positive trigger, which is a blur with high strength and a specific orientation. With positive trigger, the goal of TPatch is to be adversarial. The other is an interfering trigger, namely negative trigger, which is a blur with low strength and any orientation. With negative trigger, the goal of TPatch is to be benign. To achieve these two goals, we design positive loss and negative loss corresponding to positive triggers and negative triggers for each attack goals. The next challenge is how to improve the visual stiffness of TPatch. We intend to make the TPatch look more meaningful, for example, look like a cartoon character. A vanilla approach is to add a loss that reduces the Euclidean distance between the reference image and the patch in the pixel space. And we improve this approach by putting the loss in the feature space instead of the pixel space. Here, we use an image encoder pre-trained on ImageNet to extract high-dimensional features. From the results, we can see the TPatch generated by feature loss may look more pleasant and natural. The last challenge is how to enhance the attack robustness in the real world. We resolve this challenge from two perspectives. For the patch, we employ the common expectation over transformation method to enable the TPatch to fit with various shooting distances, angles, and light conditions. For the trigger, we apply multiple triggers in the optimization of TPatch to tailor the triggerable region. Thus, TPatch can be easier to be triggered by imperfect acoustic attacks and harder to be accidentally triggered by unintended blurs. To evaluate the performances of TPatch, we conduct both simulation and real-world experiments. In simulation, TPatch can achieve over 85% average success rate of hiding, creating, and altering attacks on various models and various target classes. Due to the time limit, I mainly present the real-world evaluation. In real-world evaluation, we consider three attack scenarios of acoustic signal injection, that is in-car, car-to-car, and roadside. In these scenarios, the victim system is composed of a driving autonomous car and a smartphone camera mounted on this car. The attack devices include a printed TPatch with a size of 6 cm by 6 cm and an ultrasonic transducer array. Note that in real-world evaluation, we focus on hiding and creating attacks of the stop sign class. To evaluate the performance in the real world, we employ the metric of consecutive attack. That is the max attack success rate in a specific number of consecutive frames. From the results, we can see the hiding attack is easier than the creating attack, and the white box attack is easier than the black box attack, but it's still feasible to attack a black box model via the transferability of TPatch in the real world. For the three attack scenarios, the attack distance are different. So we use three acoustic attack devices with different scale. Note that the minimal one only contains one ultrasonic transducer with 0.08 watts. And we conduct hiding and creating attacks in each scenario. The results show that the in-car attack achieved the best performance, and the car-to-car and roadside attack achieved comparable performances. Moreover, we studied the impact of various factors on the effectiveness of TPatch. For attack distance, we find the attack performance starts to drop when the distance is more than 5 or 6 meters, and we investigate 3 vehicle speeds up to 15 km per hour due to the safety reason. We find the TPatch can keep over 95% success rate in 50 consecutive frames. We also evaluate TPatch on 2 different cameras with different image stabilizers and find their attacking performances are close to each other. Okay, let me show you the demos of TPatch. The first video shows an in-car hiding attack. The inject blur is quite stable and makes the stop sign unrecognized perfectly. The next one shows a car-to-car creating attack. The attacker launches acoustic attacks from the left car and makes the TPatch recognized as a stop sign. The last one shows a roadside hiding attack. Although the inject blur is less stable than the one of the in-car attack, it still successfully hides a patch for a while. More demo videos are available on this website. To mitigate the TPatch attacks, we propose several possible countermeasures. From the sensor level, isolating the attacking sound or adding a secure low-pass filter can prevent the manipulation of inertial sensors. From the algorithm level, the possible countermeasures include training a robust model or detecting the distortion caused by sensor attacks. From the system level, sensor fusion with LiDAR and high-definition maps may mitigate the recognition errors. Finally, we conclude this paper. This work is the first attempt at the adversarial patch triggered by physical signals. We designed TPatch triggered by acoustic signals to realizing hiding, creating, and altering attacks against the visual recognition models, and validate its effectiveness with a real-world moving vehicle. This is all my presentation. Thanks for listening.